Hey math enthusiasts! Today, we're diving into a fascinating concept that underpins many areas of higher mathematics: limits. Limits are fundamental in calculus and are used to define derivatives, integrals, and continuity. Don't worry, it's not as daunting as it might sound. With a bit of practice and understanding, you'll find that limits are quite approachable. In fact, it's a pretty intuitive idea, and once you grasp it, you'll be well on your way to conquering calculus and beyond. Imagine the satisfaction of solving complex problems with ease. Before we get into the nitty-gritty, let me ask you a question. Have you ever been curious about how we can predict the behavior of a function as it gets closer to a certain point? Have you ever wondered what happens to a function as its input gets closer and closer to a particular value? This is where the concept of limits comes into play. That's precisely what limits help us explore. They allow us to understand the behavior of functions in a detailed and precise manner. Think of it like approaching a wall. As you get closer, you can see more details and understand its structure better. As you take steps closer and closer, you get nearer to the wall, right? Similarly, limits help us get closer to understanding the behavior of functions. Limits work similarly, but instead of distance, we're looking at the behavior of functions as their input approaches a specific point. This concept is crucial for many advanced topics in mathematics. So, buckle up and let's embark on this exciting journey to unravel the mysteries of limits. Together, we'll explore this fundamental concept and see how it opens doors to new mathematical insights. Now you might be wondering, why should I care about limits? Well, my friends, understanding limits is like having a secret weapon in your mathematical arsenal. Firstly, limits form the bedrock of calculus, a branch of mathematics that deals with continuous change. Without limits, many of the fundamental concepts in calculus would simply fall apart. From finding the slope of a curve to calculating areas and volumes of irregular shapes, calculus relies heavily on the concept of limits. Imagine trying to understand motion or growth without them. It would be nearly impossible. Secondly, limits are essential for understanding the behavior of functions. They allow us to predict and analyze how functions behave under various conditions. They help us analyze what happens to a function as its input approaches certain values, even if the function itself isn't defined at those points. This is crucial for solving real-world problems where exact values are often unknown or undefined. But it's not all about abstract math. Limits have practical applications that extend far beyond the classroom. Engineers use them to design bridges and airplanes, ensuring these structures can withstand various forces and stresses. Engineers use them to design bridges and airplanes. Economists use them to model market trends, helping to predict economic shifts and make informed decisions. And physicists use them to study the behavior of particles, which is fundamental to understanding the universe at a microscopic level. So mastering limits isn't just about acing your exams. It's about equipping yourself with a powerful tool that has wide-ranging applications in various fields. Whether you're solving complex equations or tackling real-world challenges, understanding limits will give you a significant edge. All right. Let's get down to business and define what we mean by a limit mathematically. In simple terms, the limit of a function fx as x approaches a certain value, say a, is the value that fx gets closer and closer to as x gets arbitrarily close to a from both sides, without actually reaching a. We represent this mathematically as lim xa fx equals sign L. This notation reads as the limit of fx as x approaches a is L. Essentially, it means that as x gets closer and closer to a, the value of fx gets closer and closer to L. Remember, the function doesn't have to be defined at x equals sign a for the limit to exist. It's all about the behavior of the function as x gets closer and closer to a. Let's say you're trying to measure the temperature of a cup of hot chocolate as it cools down. You can't directly measure the temperature at the exact moment it stops being hot and starts being lukewarm, right? But you can take temperature readings at intervals as it cools. As the time intervals get smaller and smaller, your temperature readings get closer and closer to the temperature at that transition point. That, my friends, is the essence of a limit. We're not interested in the actual temperature at that precise moment. We're curious about the temperature it approaches as it cools down. That approaching value is what we're after when we talk about limits. Section 5. Unraveling a limit problem, a step-by-step guide. Now that we've got a conceptual understanding, let's tackle a limit problem together. Limits are fundamental in calculus, and understanding them can open doors to more advanced topics. So, let's dive in and break it down step by step. Let's find the limit of the function f of x equals x squared minus 1 divided by x minus 1 as x approaches 1. Step 1. Direct substitution. This is often the first method we try when solving limit problems. Our first instinct is to substitute x equals 1 directly into the function. This method works for many functions, but sometimes we hit a snag. However, we encounter a problem. We get 0 divided by 0, which is undefined. This is known as an indeterminate form, and it tells us that we need to try a different approach. Don't worry, this is where the power of limits comes in. Step 2. Simplification. Simplifying the function can often help us resolve the indeterminate form. We can simplify the function by factoring the numerator f of x equals x plus 1 times x minus 1 divided by x minus 1. Factoring helps us see common terms that can be cancelled out. Notice that x minus 1 appears in both the numerator and denominator. This common factor can be cancelled out, simplifying our function. We can cancel them out, but remember, we can only do this because x is approaching 1, not equal to 1. This distinction is crucial in understanding limits. Step 3. Evaluating the limit. Now that we've simplified the function, we can proceed to evaluate the limit. Now we're left with f of x equals x plus 1. This is a much simpler function to work with. As x approaches 1, f of x approaches 1 plus 1, which equals 2. This final step confirms our solution. Therefore, the limit as x approaches 1 of x squared minus 1 divided by x minus 1 is 2. Understanding this process is key to mastering limits and advancing in calculus. Section 6. The intriguing case of undefined functions. Remember how we couldn't directly substitute x equals 1 in our previous example because it made the function undefined? That's a common scenario when dealing with limits. The beauty of limits is that they allow us to explore the behavior of functions even at points where they're not defined. It's like peeking into the function's behavior from infinitesimally close to the undefined point without actually touching it. This ability to analyze functions at undefined points makes limits incredibly powerful for understanding the nuances of mathematical functions. Section 7. Mastering limits, tips and tricks. Mastering limits, like any mathematical concept, requires practice and a few tricks up your sleeve. Here are some tips to help you along the way. Start with the basics. Ensure you have a solid understanding of functions, algebra, and graphing before diving deep into limits. Practice, practice, practice. Solve various types of limit problems from your textbook or online resources. The more you practice, the more comfortable you'll become. Visualize using graphs. Sketching the graph of a function can provide valuable insights into its behavior and help you understand limits better. Don't be afraid to seek help. If you're struggling with a particular concept, don't hesitate to ask your teacher, classmates, or online forums for clarification. Section 8. Key takeaways. Your limit cheat sheet. Here's a quick recap of the essential points to remember about limits. Limits describe the behavior of a function as its input approaches a specific value. The function doesn't have to be defined at that value for the limit to exist. We can use direct substitution, simplification, or other algebraic techniques to evaluate limits. Limits are crucial for understanding calculus, analyzing functions, and have real-world applications. Section 9. Conclusion. Embrace the challenge, conquer the concept. Congratulations! You've now embarked on your journey to understanding limits, a fundamental concept in mathematics. Remember, mastering limits is not about memorizing formulas. It's about grasping the underlying idea and applying it to solve problems. Embrace the challenge, practice diligently, and don't be afraid to make mistakes. With perseverance and a curious mind, you'll conquer this concept and unlock a whole new world of mathematical understanding.